What is quantum error correction explained simply? Imagine trying to keep a delicate glass sculpture safe in a busy workshop. Every tiny bump or jolt could shatter it. That's similar to what quantum computers face with their qubits. They are super sensitive and prone to errors from noise and imperfections. To make quantum computers reliable, scientists use a method called quantum error correction. Quantum error correction is a set of techniques that protect the fragile quantum information stored in qubits. Because qubits can be affected by tiny disturbances, the goal is to catch errors before they ruin the computation. But here's the tricky part. Measuring a qubit directly can destroy its quantum state. So, quantum error correction finds clever ways around this problem. It works by spreading the information of one logical qubit across many physical qubits. Think of it like copying a message onto multiple pages. If one page gets smudged or torn, you can still recover the original message by looking at the others. But in quantum computing, it's more complex because qubits can be in superpositions, meaning they can be in multiple states at once, and they can be entangled with each other. To detect errors without destroying the quantum information, quantum error correction uses special measurements called syndrome measurements. These measurements don't look at the actual data directly but instead check for error patterns. If an error is detected, the system applies a correction, similar to fixing a broken link in a chain. Some well-known codes used in quantum error correction include the shear code, which uses 9 physical qubits to protect one logical qubit and can fix both bit flip and phase flip errors. The Steen code uses 7 qubits and is designed to be fault-tolerant, meaning the process of fixing errors doesn't introduce new ones. The surface code arranges qubits on a 2-dimensional grid and is promising for building large, reliable quantum computers because it can handle higher error rates. Quantum error correction is an ongoing process. It involves repeatedly checking for errors through syndrome measurements and then applying corrections. This process helps maintain the quantum state for longer periods, allowing quantum computers to perform more complex calculations accurately. Right now, quantum hardware has relatively high error rates, which makes error correction essential. Without it, quantum computations would quickly become unreliable. By implementing quantum error correction, scientists are making strides toward fault-tolerant quantum computers that can solve problems in cryptography, material science, and optimization. In simple terms, quantum error correction is like a safety net for quantum information. It encodes data across multiple qubits, detects errors without destroying the quantum state, and fixes mistakes as they happen. This technology is key to turning quantum computers from experimental devices into powerful tools that can handle real-world problems reliably.